this video we'll talk about geometric probability. We've got really two different types of problems that we need to think about with geometric probability. Geometric probability related to lengths, and then geometric probability related to areas. So if we had a segment that, or maybe, yeah, a segment AB that is 12 units long, and a point C such that AC is 2 units long. If we were to ask the question, what's the probability that a point chosen randomly on segment AB falls within 1 unit of C? To answer this question, we really need to look at the lengths of some segments. Well, if the point falls between 1 unit to the left of C and 1 unit to the right of C, that would be considered like a winning choice, a successful choice. So our probability would be 1 unit to the left plus 1 unit to the right, that's 2 total units, over the total possible place that we could select things from, which would be 12. So 2 over 12, and that's 1/6. So for this particular diagram, if a point chosen at random on segment AB, we're looking to see if it would be within 1 unit of C, that would be 2 over 12. Now, sometimes you might see this written in a different way, maybe on a number line. Where A is at 0, C is at 2, and B is at 12. It's really the same problem if I ask, what's the probability that a point chosen on segment AB falls within 1 unit of C? For some reason, students like to put in tick marks and count the tick marks, and students will say, though, there's 1, 2, 3 places that would work out of 1, 2, 3, 4, well, it would be 13 tick marks from A to B. However, that's not what we're looking at, because tick marks are excluding all of the spaces here and all the space here. Those would all still be within 1 unit from C. So we need to not think about individual points along the line. We really need to be thinking about those lengths. So the same problem as before should have the same answer. Again, we're looking for all of these points, so that's a length of 2 units over the whole length of 12 units, which again is 1/6. So the probability, whether it's on a number line or wasn't drawn on a number line, it's the same question, should be the same. So that's probability regarding lengths. There are some things we need to be careful about on this same question. If I were to ask, what's the probability that it falls within 4 units of C? So again, if we have A, C, and B on our number line, 0 to 12. So on segment AB, within 4 units of C. The trick on this one is you can't go 4 units to the left of C and still be on segment AB. You can only go 2. But you can go 4 units to the right. So our location for successful choices isn't 8 units long, as some students might think, it's 6 units long. Now, our total places we can choose from on segment AB is still 12. So our probability is 6 over 12, or 1 over 2. Now the next thing is geometric probability when we're thinking about areas. So a target. So if a point is chosen at random on a large circle, what's the probability that it falls within the shaded region? Well, to do that, we need to find the area of the shaded region. And once we have the area of the shaded region, we need to know the area of the big circle, and we would do our fraction that way. Probability in this case is anywhere on the circle is where our point could be chosen. So that's our total possible places, that's the denominator. So if our radius was 14, it would be 14 squared pi r squared for the circle. If the radius of our inner circle was 3, it would be 3 squared pi for the radius of our inner circle. So you would do the area of the shaded region divided by the area of the total place that you can select the points from. The problems like this could get a little bit more complicated. You might see instead of the shaded region being the outer circle minus the inner circle. In which case, again, you would have the same denominator, 14 pi if that's the same radius. And if our inner circle still has the radius of 3, our successful locations now is not 3 pi squared. Our successful places is the rest of the circle. So that's actually 14 squared pi minus 3 squared pi. So we could do a little bit of simplifying. It's 14 squared. 196 minus 9. So we would have 187 pi over 196 pi. So we can type that in, 187 divided by 196, the pi's do cancel. So our decimal approximation would be about 0.95. And as a fraction, it was already reduced. So, finding the area, or finding the probability of it falling within the shaded region, you need to find the area of the shaded region and divide by the total area of the shape where the point can be selected from. And that's how you would find geometric probability. There's two different types to think about. There's geometric probability when we're looking at areas, and then there's geometric probability in relation to lengths on a number line or segment.